GeeksforGeeks. In this video, we will talk about the 0-1 knapsack problem. So the 0-1 knapsack problem says that given weights and values for n items, you have to put these items in a knapsack of capacity W in such a way so that we get the maximum total value in the knapsack, while ensuring that we don't exceed the items that we put inside the knapsacks. Their total weight do not exceed the weight capacity W. So in other words, we are given a value array, a weight array, and the knapsack weight capacity W. And our objective is to find the maximum value subset of value array such that the sum of weights of this subset is either smaller than or equal to W. So we call it the 0-1 knapsack problem because of the 0-1 property. So the 0-1 property says is you cannot take a fraction of an item. You either take the item as a whole or you don't take it at all. So here is an example. So we are given a value array that has the values of 3 items, and we are given a corresponding weight array and also the knapsack weight capacity. And so now we have to find out which of these items do we put in the knapsack so that while staying under this weight constraint, we obtain the maximum value. So on the right side, I've written all the possible combinations of the items that we can put in the knapsack, and you can see the corresponding values that they yield for every possible weight. So of course, since none of these items are heavier than 50 units, so we can try to put more than 2 items. So if I try combining items, I see that I get a weight of 20 plus 10, that gets me a value of 160. So now for weight 30, I have 2 options. Either I get the value of 120 or 160. So obviously between these I prefer 160. Similarly, going up, I see that I can get a weight 50 by combining the item with weight 30 and 20, and for this I get a value of 220. And I can't put all these 3 items because they will exceed the weight capacity. Sorry. So what we mean is that as we keep on increasing the weight while we do not exceed the weight capacity, we see what is the maximum value that we can achieve. So for this problem, our answer is going to be 220, because while staying within the weight constraint of 50, we can obtain the maximum value of 220, because that is the maximum of all these 6 values. So let us try to come up with a nice solution to this problem. Let us discuss this nice solution over here. So what we do is we begin with considering all possible subsets of item, and we calculate the total weight and the value of all subsets. And once we are done doing that, what we do is we consider only those subsets whose total weight is either equal to or smaller than W. So, and after that, the next step is from all of these subsets, we pick out the maximum value subset. Now, when we say to consider all subsets of items, what we are really saying is for every item, there can be 2 different situations. Either we include this item in our optimal subset or we do not include this item in our optimal subset. So let us see what this translates to. So what this basically means is we have a problem where we are given n items and we want to find out an optimal subset of these n items. So in the beginning, we have n items and a weight constraint, and we have to do some operation so that we decide whether we can keep the current item in focus in our optimal subset or not. So one by one, we will consider if we can include a given item in our optimal set or not. So how do we go about it? So basically, in order to obtain the maximum value, we have to make a choice in the following way. We begin with reducing this problem to not selecting the nth item and instead moving on to n-1 items, while reducing the problem to that of n-1 items, and the weight remains same. So basically we are considering the case what if we do not include the nth item and we just solve this problem for n-1 items and W weight. Do we get an optimal value? Do we get a bigger value? And the other case is we take the nth item and then we reduce our problem to obtaining the maximum value of by using n minus 1 items, but this time we reduce the weight capacity by the weight of nth item, and we also count the value of nth item because we are including it in our optimal subset. And we keep on doing this repeatedly until we keep on repeating this until we are not left with any more items. We are done considering all the items. Achha. And also there is this thing is, if weight of the nth item itself is greater than w, then of course we can't include it in the optimal subset, which means that we must leave this item and proceed with n minus 1 items. So here is a recursive solution. So let's see what's happening here. We have this knapsack function over here, which is going to return the maximum optimal value, and this is given the knapsack weight constraint as a parameter, the weight array, the value array, and the number of items. So as you can see, we have 3 cases over here. Now this is very similar to what we just discussed on the last slide. So the case 1 is it's pretty straightforward. The base case over here is, if we have n is equal to 0 or weight is equal to 0, we return 0. So basically, if we don't have any items to put in the knapsack, we won't get any value, so we return 0. If the knapsack weight capacity itself is 0, we can't put anything inside the knapsack. Unless we have some items which has the weight capacity 0, but that's not really a general case. So in either of these cases, we end up returning 0. If there are no items or the knapsack weight capacity is 0, we return 0. Moving on, next we perform this test at this second level. In the second part, what we do is we check if the weight of the nth item that we are considering, whether do we include this item in our optimal subset or not. So we check if the weight of this item itself exceeds the w weight capacity. If it does, we exclude it. If it doesn't, then we move on to the third case. Now third case is the one where the weight of the nth item does not exceed the weight capacity, and now we want to see if the nth item forms a part of the optimal subset or not. So now we make 2 recursive calls to the knapsack function. In this case over here, we are including the nth item in our optimal subset, and in this case we are not including the nth item. So we recursively call the knapsack function and we wait for the, we recursively call this knapsack function in these 2 ways, and then when we obtain their values, we compare, and whichever one of these values is greater, we return that value. So let us do a dry run of that the solution that we just saw. So we'll be using the same example. We have the same weight array, same value array, and same knapsack weight capacity constraint. So we begin with something like this. So k 3, 50 means that we have 3 items, and 50 is the knapsack weight capacity. So when we call k 3, 50, this problem is divided into these 2 parts. In case 1, we consider including the third item, the value of which is 120, and in the second case, we consider excluding it. So you can see that when we include the third item, we are accounting for its value, which is 120, and we are reducing the knapsack problem by 1 item, and we are reducing the weight of the weight capacity of the knapsack by the weight of the third item. So this becomes 50 minus 30, 20. And in the other case, since we are simply excluding the third item, we reduce the number of items by 1 and the weight capacity remains same. And so on, we do this repeatedly until we arrive at a base condition where either the number of items is 0 or the weight itself is 0, in which cases we return 0. We reach one of those base cases. So as you can see later on, so if you take a look at these 2 branches, you know that this max will receive a 60, and then if you take a look at these 2 branches, you know that these 2 will result in a maximum of 100. So basically k220 will get you a 100. Similarly, if we come over this side, you can see that if you take a look at these 2 branches, you see that the max receives a 60, and similarly this max also gets a 60, and this max then gets 160 because 100 and 60 for this max. However, the second branch is only getting a 60, so 160 is greater in this case. So k2, 50 yields us 160. So of course, if we add 100 and 120, we get 220, which is our answer. So this is how the algorithm runs. So the time complexity of this algorithm is going to be big of 2 raised to n, because we have n items, and for every item we are making a choice whether we include that item or not. So that's how we get this time complexity. And since we are not using any extra space, so our space complexity stays big of 1. Now there is this interesting thing that you can see here is if we call the knapsack function in this case, here's another example where we have 3 items, all of those have the same weight, and the values are 10, 20, 30, and the weight capacity is 2. So so in this case, as you can see, we began calling the knapsack function with the parameters 3, 2. 3 is the number of items, 2 is the weight capacity. And you see that on both of the sides, so at every step you see that the tree is divided into 2 parts. The left part is when we exclude the nth item, and the right part is when we include it. So this is where we include the nth item, this is where we exclude the nth item, and this is repeated for all the subtrees. So if you look down here, you see a k1, 1 appearing over here, and a k1, 1 appearing over here too. And so this means that we are solving the same problems on both the branches. And if you further look down, you see that this whole subtree is actually repeated. Sorry. So this is a very small example. I mean, for a bigger example, we can see that there will be bigger subtrees, and all those computations will be unnecessarily repeated. So what we see here is we like this knapsack problem satisfies the overlapping subproblems property. So since now that we have seen that the 0-1 knapsack problem satisfies the overlapping subproblems property, and and it also has the optimal substructure property. So optimal substructure comes where we repeatedly solve the same problem. So you saw that we were changing the parameters of the knapsack function, and yet we were recursively calling the same function again and again and arriving at a solution. And then we also saw that some of the problems were overlapping also in different branches. So this makes the 0-1 knapsack problem a dynamic programming problem, because a dynamic programming problem is anything that has the 2 properties, the overlapping subproblems and the optimal substructure. So let us see that if we can come up with an algorithm where we avoid all these recomputations of the same subproblems, and maybe you can build a temporary array in a bottom-up manner, and then we can just look up the values for problems that we have already solved, so we don't solve the same problems again and again. So here is the dynamic programming approach. So we have this knapsack function over here. You have the weight capacity, the same weight array, the value array, and the number of items. Now we have this n+1 into w+1 dimensional array. Now this is where we are going to store all the solutions. So whenever we solve a problem, let's say we solve k1, 0, or we solve k0, 1, so we will put the solutions, the values that we obtained from k1, 0. Sorry for the bad handwriting. So if we have solved k1, 0, we will just update the value of k1, 0 as 0, and so on. So moving on, we will follow a bottom-up manner, and at every step we will update one cell of the this K matrix, and this is how we will eventually arrive at our solution. So we have 2 loops over here. The first loop runs n times, and the inner loop runs w times. So the first loop is simply to show that we are considering one by one all the items, and the second case is considering the case where we are trying out different possible weight scenario, and we are finding the solutions to these combinations, and we are storing them. So in the inner loop, we see that if I is equal to 0 or the weight is 0, so basically if the number of items is 0 or the weight is 0, we knew that the solution was to return 0. So we are simply storing 0 in our matrix. So all the k0, w or all the kw, 0, the first row and the first column of our K matrix are going to be all zeros. So moving on, in the second case, so here in now in the second if, we check whether the weight of the ith item, which is for the given problem the nth item. I mean, if so at every step of this loop, what we are really doing is we are solving this problem, k I comma w. So at every iteration, what we are really doing is we are considering whether we should be including the ith item in our optimal subset or not. So the first thing that we are doing is we are checking whether the weight of the ith item is exceeding the knapsack weight capacity or not. If it's not, then we move on to the optimal substructure solution part. So as if you remember from the recursive implementation or from the earlier discussion that we had about the structure of this problem, the solution. So we saw that whenever the weight of the ith item is not exceeding the capacity, we make a choice. We consider two cases. Case 1 is when we consider including the ith item, and case 2 is when we think of excluding it, and we see what we get. So now here if the weight of the ith item does not exceed the capacity, what we do is we make a choice. So here we are calling the max function with two parameters. Now parameter 2 is kia minus 1 comma w. So this is where we are simply excluding the ith item, and we are just saying that what if we exclude the ith item, do we get a better value, do we get a better optimal solution? And over here on the left, as you can see, is we are considering what happens if we include the ith item. So we count we add its value to the sub problem where we have ki minus 1 and we have the weight capacity reduced by the weight of the ith item. So we see which of these two values is the greater one, and then we assign that value to ki comma w. However, if the weight of the ith item is greater than w, then in that case we of course can't consider including the ith item in our optimal subset. So we go ahead with the second option, and eventually finally when we are done building this whole k array, we return k n comma w, which is the solution to our problem. So let's take a look at the dry run of this dynamic programming approach. So again, I mean, not in a recursive sense, but again we are calculating the solutions to all these problems, except what's different this time is you can see that we have a k 0 comma 20 over here, we have a k 0 comma 20 over here too. But what happens when we are using the dynamic programming approach, we are not solving these two problems twice. So the first time we came across this problem, we updated, we calculated the solution and we stored the value in our two-dimensional array. And the next time we came across k 0 comma 20, we simply used the existing value. So this is how our time complexity is reduced from big O of 2 raised to n to big O of n into w, which is of course way better than big O of 2 raised to n. However, in this case, since we are using an n cross w size array, our space complexity does increase to big O of n into w over big O of 1 in the previous case, but I mean we make a huge improvement on the time complexity part. So and you can see that we will end up arriving at the same solution. So that will be all.